Hello, a great welcome to this series on machine foundations. This is lecture 6 of the series. So here I will explain you the damped force vibrations. So before getting into the details, please ensure that you subscribe to the YouTube channel by clicking the button on the right corner. So let us get into the details. So as you can see, today we will analyze in detail the response of a single degree of freedom system that is subjected to a harmonic load. As you can see that this is a system with a stiffness K, the mass M, the damping C, and the response is given by Ut, and the system is subjected to a harmonic load defined as Pt equal to P0 into sine of omega t. Here remember that P0 is the amplitude of the excitation force and omega is the excitation frequency. And here we define one more term, that is omega d, known as the damped natural frequency. That is, as usual, we know that is given by omega in the square root of 1 minus of c square. In the same way we did in the previous videos, the dynamic equation of equilibrium for such a system can be easily written as m into u double dot plus of c into u dot plus ku is equal to pt. Obviously this do not require any kind of explanation, and we know that the total solution ut is given as uc plus of up, where we know that ut is a total response and uc is a complementary solution. Obviously we know that this is nothing but the solution corresponding to the free vibration response given by m into u double dot plus of cu dot plus ku equal to 0. And obviously we have solved this equation in our earlier videos, and we know that the corresponding complementary solution is given by uct equal to e raised to minus of c into omega n into t into a cos of omega dt plus of b into sine of omega dt. And here please remember that the solution consists only of terms relevant to the natural frequencies. For example, you can see that it consists of omega n, it also consists of omega d, and the term excitation frequency omega do not appear in this equation. It is just because this corresponds to a free vibration. Now let us discuss about the particular solution. The particular solution is given by up is equal to g1 into sine of omega t plus of g2 into cos omega t. Now we have an expression for uc, we have an expression for up, and we can obtain the total response ut as uc plus up. Okay, now we know that the particular solution up, it should satisfy the equation m into u double dot plus k into u dot k into u plus of c into u dot is equal to p 0 into sine of omega t. This means that we can substitute the expression of up in that equation for equilibrium and easily obtain the particular solution upt as upt is equal to ust divided by 1 minus beta square the whole square plus 2c beta the whole square into 1 minus beta square into sine of omega t minus of 2 into c into beta into cos of omega t. Remember, as particular solution is a solution corresponding to the forced vibration, it is important to note that this equation do not have any terms like omega n. Instead, it has a term containing omega, which is nothing but the excitation frequency. Now, as you can see that the equation has a term ust. Let us see what is this ust. This ust is defined as a static deformation that is given by p0 by k. We know that p0 is nothing but the amplitude of the excitation force, and accordingly, if a static load p0 is applied onto the system, we know that the corresponding deformation will be p0 by k. That is why it is called ust, that is the static deformation if a load of p0 is applied onto the system. And beta is another term, and remember, it is a focal term in the analysis of damped forced vibration. And this frequency ratio is obtained as the ratio of two frequencies. That is, in the numerator we have the excitation frequency, and in the denominator we have the natural frequency omega n. So beta is the frequency ratio. Now remember that in the previous slide we have seen that the total solution is nothing but it's a complementary solution plus the particular solution. Now the problem is that in the complementary solution, the transient component, it dies out due to the damping effect, which means that the total response is obtained solely by the particular solution, and it is very clear that this particular solution provides us the steady state response UP, right? Therefore, in our discussions, we will focus only on the particular solution UPT, that is, the total response is equal to the complementary solution. The complementary solution we will not consider because that component is dying out with time, and we have got only a steady state response UPT. So now let us see that how the UPT is obtained. So UPT is obtained from this equation. Let us try to simplify this equation a little bit further. So first we shall proceed to define a term capital D, and this capital D is defined as the dynamic magnification factor. So remember that in the case of forced vibrations, that is we are talking about the damped vibrations, the response is critically governed by two parameters. One is the frequency ratio beta, and the other one is the dynamic magnification factor capital D. So now substituting this expression for capital D into the particular solution, we have the UPT that is given by UST into capital D, this multiplied by 1 minus beta square into sine of omega t minus of 2c beta into cos omega t, this divided by square root of 1 minus beta square the whole square plus 2c into beta the whole square. So means that this is how we define the steady state response. Okay. Now let us try to simplify this expression further again. So as you can see that the particular solution UPT, it is governed by two terms, or rather three terms. One is the dynamic magnification factor capital D. The second one is the frequency ratio, and then the third term is the damping ratio C, and finally we have got one more term that is nothing but the excitation frequency omega. So all these four terms will affect the response of the system under forced vibration. Now let us try to simplify this equation. Now what we'll do is that we will draw a triangle, that's a right angle triangle, with the base as 1 minus beta square and the opposite side as 2 into c into beta, which means that the hypotenuse can be written as square root of 1 minus beta square the whole square plus of 2c into beta the whole square, which means that we can write down with respect to this right angle triangle the cos theta is equal to 1 minus beta square divided by square root of 1 minus beta square the whole square plus 2z into beta the whole square. And again sin theta can be defined as opposite side, that is a 2c into beta divided by square root of 1 minus beta square the whole square plus 2c beta the whole square, which means that the particular solution, that's the steady state response, is given by UPT, that is equal to UST into D into cos theta into sin omega t minus of sin theta into cos omega t. And remember that this expression is obtained by substituting in the expression for UPT we have discussed in the earlier slide the values of cos theta and sin theta. Okay. Now, which means that this expression can be further simplified to UPT is equal to UST into D into sine of omega theta minus of theta. Now look here, this expression is very simple. That means we are now able to represent the steady state response in a more easy to digest form. That is, UPT is equal to UST into capital D into sine of omega t minus theta, which means that the steady state response can be represented by a sinusoidal plot. Obviously, the amplitude of the motion is given by the static deformation UST into capital D. And remember here that theta is the phase angle by which the response lag behind the applied force. So in order to better understand the influence of the frequency ratio beta on the dynamic magnification factor D, here I have made a simple plot. As you can see that on the x-axis is the frequency ratio beta and on the y-axis is the dynamic magnification factor capital D. As you can see that the plots are made for various values of the damping ratio C, right from C equal to 0 up to C equal to 1. Now here we can make some important conclusions. That is, the effect of the damping as we perceived is to limit the maximum amplitude of vibration. For example, as you can see that at C equal to 0, that is at zero damping, that is equal to an undamped condition, the dynamic magnification factor capital D tends to infinity, which means that the amplitude of motion will also be infinity. Now, as you can see that when the damping ratio is increased to 0.1, the amplitude of motion, it is limited to a very lower value. For example, you can see that at C equal to 0.1, the dynamic magnification D equal to 5, which means that for a system with a damping ratio of 0.1, the amplitude of motion will be UST into D. D here it is 5. 5 into UST. What is UST? It is nothing but a P0 by K. Now, as you can see that irrespective of the values of the damping ratios considered, the peak value of the dynamic magnification factor, or in other words, the peak value of the amplitude takes place around a value of a frequency ratio that is equal to 1. Or in other words, irrespective of the values of the damping considered, the resonance or the maximum displacement always occurs around a value of beta, that hovers around beta is equal to 1. Now we will see how to obtain the value of the frequency ratio beta that corresponds to a peak value of dynamic magnification factor capital D. Okay, so let us find out what will be the value of the frequency ratio beta, that is beta peak, that results in a peak value of capital D. Remember, this is nothing but this is a plot of beta versus capital D for an assumed value of the damping ratio. And now we would like to find out what would be the peak value of the frequency ratio for which the dynamic magnification factor and hence the amplitude will be maximum. So in order to find out this frequency ratio, let us consider the basic expression for the dynamic magnification factor capital D. Capital D can be written as 1 divided by square root of 1 minus beta square the whole square plus 4 into c square into beta square, which can again be written as 1 divided by square root of 1 plus 4c square minus of 2 into beta square plus beta raised to 4. Now obviously from our knowledge in calculus, we know that for the maximum value of D to occur, the value of beta should be such that the first derivative of D with respect to beta should be equal to 0. So let us differentiate this expression for capital D with respect to beta, which will provide us a term minus of half into 1 plus 4c square minus 2 into beta square plus beta raised to 4, the whole raised to minus 3 by 2 into 2 beta into 4c square minus 2 plus of 4 into beta cubed, which further simplifies to half into d cubed into 4 beta into 1 minus 2c square minus of beta square. Now, for maximum value of d, obviously we know that the equation, the first derivative of d with respect to beta should be equal to set equal to 0, which means that we get, for an assumed value of the damping ratio c, the peak value of d, that is the peak value of the amplitude, occurs at a frequency ratio beta, which is equal to beta equal to square root of 1 minus 2 into c square. And for an assumed value of damping ratio c, the peak value of the dynamic magnification factor d peak is equal to 1 divided by 2c into square root of 1 minus 2c square. So here I have made a plot. So I considered various values of the damping ratio, and here I made a plot of beta peak versus d peak. So as you can see that here, as the beta value, as the frequency ratio is increased, we find that obviously the correspondingly d peak value also increases, right? Now let us go a little bit deeper into the phase angle. In the earlier slide, we have defined the phase angle theta, which is nothing but it's the angle by which the response of the system lags behind the applied force. So, and we have derived sine theta is equal to 2c into beta divided by square root of 1 minus beta square the whole square plus 2c beta the whole square. Now, as you can see that the phase angle is directly a function of the damping ratio c and the frequency ratio beta. So here I made a plot of frequency ratio beta versus the phase angle theta for various values of the damping ratio c. So let us make some important conclusions out of this plot. So here I have written some important conclusions. The phase angle by which the response lag behind the applied force is essentially due to damping. So this is very clear to us. So we can see that from this curves that the damping has got a very significant influence on the phase angle. Now let us consider two systems. One is undamped systems. So undamped system means the damping ratio C must be equal to 0. So as you can see that for C equal to 0, for beta, that's a frequency ratio less than 1, theta will be 0. That means for undamped systems, for frequency ratio less than 1, the phase angle theta will be 0, which means that the applied loading and the response will be in phase. And also we find that for beta greater than 1, if you consider we are talking about C equal to 0 undamped system, so you can find that for beta greater than 1, the phase angle theta will be equal to 180 degree. Now coming to the damped systems, we can say that theta increases from 0 to 90 degrees. For example, if you are talking about, let us say that we are considering the damping ratio of 0.2, means that I am talking about the red curve. So here one thing is very evident for us. As the frequency ratio increases from 0 to 1, the phase angle theta, it increases from, you can say that it increases from 0 to 90 degrees. Now for the frequency ratio beta that is greater than 1, you can see that the phase angle approaches towards 180 degrees. That means as the frequency ratio increases from 1 to infinity, the phase angle theta, it approaches a value of 180 degrees. Now let us consider 3 cases in order to get a better interpretation of the force vibration. So first case 1, we'll consider beta very much less than 1. That means the frequency ratio is very much less than 1. What do you mean by the frequency ratio very much less than 1? That is, the excitation frequency is very small when compared to the natural frequency. Or in other words, this represents a very slowly applied load. So if you substitute beta very much less than 1 into our basic equations for the dynamic amplification factor D and the phase angle theta, we find that for this case, the dynamic amplification factor or the dynamic magnification factor D in such a case will be approximately equal to 1 and the phase angle tends to 1. Which means that for such a scenario, the particular solution UPT can be written as UST into D into sine of omega t minus of theta. Substituting the value of D and theta, we obtain for a slowly applied load UPT is equal to UST into sine of omega t. So let us make the conclusions. Now here we can see that from this equation UPT is equal to UST into sine omega t, we can see that the displacement, or in other words the response of the system, is in phase with the applied loading. You can say that is UPT is equal to UST into sine of omega t. That means the response is in phase with applied loading. And further, we find that here, what is UST? UST is nothing but P0 by K. Now in such a case, the amplitude of the vibration will be UST, which is nothing but P0 by K, as I have already marked over here. And this means that for a very slowly applied load, it is the stiffness that controls the motion. So as you can see that on the same plot, in order to have a better interpretation, I have plotted both the applied load. The applied load, it is marked using a red line, P0 into sine omega t, and the response is shown over here, that is indicated by a blue line. As you can see that both the applied load as well as the response are in phase, and in the case of a slowly applied load, the amplitude of the vibration is essentially UST, that is a P0 by K. Now let us go for another case, that is beta very much higher than 1, which means that the excitation frequency is very much higher than the natural frequency, which means that we are talking about a very rapidly applied load. So if we substitute a scenario beta very much greater than 1, then substituting this value of a beta, we obtain D equal to 0 and theta tending to 180 degree. And now here, I would like to tell you that when beta is very large, the term beta raised to 4 in the equation of 4D, which I have discussed in the previous slide, and that becomes a significant, and accordingly we can approximate the term for the dynamic amplification factor capital D as 1 by beta square, which means that the response of the system UPT is given by P0 by K beta square into sine of omega t minus of pi. Remember, pi is nothing but that corresponds to a phase angle of 180 degrees. And now making substitution, we know that K is omega n is nothing but a square root of K by m, which means that this term can be simplified to P0 by m omega square into sine of omega t minus pi. Now let us make some interesting conclusions. Now here, as you can see that UPT, the final equation is P0 by m into omega square into sine of omega t minus of pi. This means that the response of the system, it lags behind the applied force by 180 degrees, or because we know that the phase angle is 180 degrees. And here, as you can see that the amplitude of the motion is P0 by m omega square. That means I have got a term m, that's a mass, which means that for such a system, that means where the load is applied very rapidly, the response is controlled by the inertia. So to get an interesting visualization, I have made a plot of the system response as well as applied load on the same graph. As you can see that the response is lagging behind the applied force by 180 degrees, and the amplitude of the response in this case is given by P0 by m into omega square. It means that we consider two cases, beta very much less than 1, beta very much higher than 1, and finally, accordingly, we have got only one more case to consider, that is what happens at beta equal to 1, that is the frequency ratio equal to 1. So this is our case 3, beta equal to 1. Now what we'll do is that for this case, we'll write the total solution including the transient term also, and obviously you know that the solution that includes the transient term, that is also depends on the initial condition. So we will consider a zero initial condition, for which we can write down the total response ut as ust into 1 divided by 2c into e raised to minus of psi into omega nt into cos of omega dt plus of psi divided by square root of 1 minus c square into sine of omega dt minus of cos omega nt. Remember that the first term is a transient component and the second term is a steady state component. So now, as you can see that we know that under an undamped vibration, what happens? We know that at a frequency ratio beta equal to 1, the amplitude tends to infinity. But if we consider an undamped vibration, it is clear that the damping lowers each peak and limits the response to a bounded value as shown in the figure. Look here. Here I have made a simple plot, that is along the x-axis I have considered the time t, and along the y-axis I have considered a ratio, the response ut divided by ust, and this equation is plotted for a damping ratio of c equal to 0.05. So as you can see that as the cycles of motion builds up, we can say that the amplitude of the motion or the response in each cycle, it goes on increasing. But remember, the system has a damping, which means that such an increase cannot repeat infinitely. And after some cycles of motion, the amplitude should get contained to a limiting value. And this limiting value, as you can see that it is nothing but 1 divided by 2 theta. That is already given over here. So for example, for a damping ratio c equal to 0.05, obviously we know that this limiting value or the steady state amplitude is 1 divided by 2 into c, which means that this is 10. That means if we consider a system with a damping ratio of 0.05, the steady state amplitude which happens after a few cycles of vibration will be nothing but ust, which is nothing but p0 by k into 1 by 2c. 1 by 2c is 10. That means in this case the peak amplitude will be 10 times the static amplitude. And remember, this is a case of beta equal to 1. Thus we come to a very important conclusion. Even at a resonance, the effect of the damping is to limit the peak value of the amplitude to a steady value, which is nothing but 1 divided by 2c. So this is how the amplitude helps, or the damping ratio helps to improve the performance of the system under a forced vibration. I think that's all regarding this presentation. Thanks a lot for listening. If you have any kind of queries, because there are many equations, obviously I could not explain the derivation of every equation. So if you have any queries, etc., please write it on the comment box and I will surely provide you a reply. So thanks a lot for listening.